This lesson will hopefully be sort of a review. We're going to talk about law of sines, but you probably never derived it, or if you had, this will be a little refresher. So what I recommend is that you print this out or copy down what's on the top of the homework sheet and kind of go through this with me. I'm going to derive where the formula comes from and how we can use it. So here's a scenario where, and big letters are angles, little letters are sides. I left B off intentionally. So here's a scenario where we've got an angle and a side across from it, and another angle and the side across from it as well. Where I want to start, and I'll often say drop a plumb bob. If you've ever done any construction, it's a weight on a string. You drop it from the ceiling, and it tells you the spot that's directly below it if you want to get a wall straight, something like that. So I'm going to drop a plumb bob right here. It's a perfectly straight up and down line that's going to be perpendicular with the floor. So I'm basically just creating a 90-degree angle right here. That's the idea, creating an altitude if you're thinking about geometry. And I'm going to call that side X. So what I can do now is I can say, all right, well, sine of A is X over C. And I can also say sine of C is X over A. And then since both of those involve X, they're both kind of centered around the same line, I can solve each one of these for X. So C sine A is X, and A sine C is also X. Which means that these two pieces are equal, because they're both equal to X. So C sine A is A sine C. And what I'm going to do is divide by the side on each piece of the equation. So divide both sides by C, divide both sides by A. Now, if that's too much at one time, just take it one piece at a time. So at the end, sine A over side A is equal to sine of C over the side length C. And that's it. That's your law of sines. You take the sine of any angle divided by the side across from it, and that same ratio is, or that ratio is going to be the same throughout the whole triangle. And if we want to work with this some more, we could also prove that sine B over B is the exact same ratio. So again, that's what it turns out to be. If you take the sine of any angle and divide it by the side across from it, that ratio will be the same throughout the entire triangle. So we could pick any side and any angle across from that side and set up a law of sines. And usually you only do two at a time, but I just put all three here so you can kind of pick which two you have to work with. So let's run through an example. Let's say I've got that angle and that side across from it. I want to find this angle, but I've got this side across from it. So I can set it up this way. I can say sine of A over the side across from it is equal to sine of 81 over 37. All right, so at this point I want to solve for A. So I'm going to multiply both sides by 25. So sine of A is going to be sine of 81 times 25. And let me make sure that's distinct, that 81, you're taking sine of 81, the angle, and multiplying the result by 25. So now we get this ratio, 0.667 and some other stuff. And if I go back, that means sine of A is equal to that ratio. I'm just going to say 0.6 to keep it simple here. So I'm going to need to take an arc sine, which I'm just going to abbreviate as like a sine inverse. I think it's easier to write that way. Arc sine undoes sine. I would always just go up and highlight all those decimals so you get a better answer. And about 41.9 degrees. Need to run through a scenario with you called the ambiguous case. Now, I've got a workaround for this so we can completely avoid it. The problems I'm giving you are not really set up to have to think too much about this or deal with it. Just be aware that it can happen. And as you go further in math, it may come up, it may not. It just really depends on what kind of field you get into. Honestly, you're very likely to never see this again in your life. Seriously, if you take a lot of math stuff, you may never deal with this. So I'm just going to show it to you to remind you about it. So it's one of those things that you're sort of aware of, but you know a workaround to get through it. So here's the scenario. Pretty similar setup. I've got 25 degrees here. Let's go ahead and enter in what I've got. 25 degrees. This side's 10. This side's 23. And I want to figure out what that angle B is. Now it looks kind of obtuse. Now keep that in mind. It looks kind of obtuse. And we'll come back to that. It's going to be important. So let's set up our sine, the law of sine ratio. Sine 25 over 10 is going to equal sine of B over 23. So pretty similar beginning here. Multiply by 23 on both sides. All right, so I've worked it all out. I've got 0.972. So let's kind of go back and fill this in. Sine of B is about 0.972. Of course, I'm going to keep all the decimals when I do this in the calculator. So let's figure out what angle B's got here. I just kind of did that from geometry, but you don't have to put an angle symbol if you don't want to. All right, well, let's see. Take the arc sine of that result. See what we get. Make sure you are make sure you're in degree mode. I get 76.4. Now, remember what we talked about in the beginning? I said it looks obtuse. That's definitely not an obtuse angle, but man, that triangle sure does look obtuse. So something feels off here. All right. So if I did a little, there's a lot of ways we could approach this. Let me kind of give you maybe a quick way to think about it. If I graph a sine wave, and I want to know where sine is 0.97. So we know sine peaks out at 1. So it's pretty close to the top. But the point is, there are going to be two angles where sine would be 0.972. Now we learned from arc sine that it's got to be a function. Arc sine would have to pass the horizontal line test, or at least sine would. So we had to cut it off here at pi over 2. So arc sine never gives you an angle bigger than pi over 2. But this angle sure does look like it's bigger than that, or 90 degrees. This angle looks bigger than 90 degrees. So kind of a little bit of symmetry, probably the quickest way to do this. See how far this is from 90 and add that to 90. So what I just did was I took 90 minus the answer I got, the 76 degrees. Found that difference and then I added it to 90 to kind of get some symmetry going on. And I'm getting about 103.6. And just to kind of confirm this, I'm going to take the sine of both of these and I'll put them on the screen together so you can see that they're really the same thing. So there they are. There's a sine of 76.4, sine of 103.6. Again, kind of thinking about the graphs, probably the easiest way to think about it. There's two angles that you get that same y value, the same ratio out. So these are just as valid as one another. Both angles could be the right answer. A sort of visual way to see how this might play out. If this angle is 103, then this is what it's going to look like. But this side right here could maybe kind of be swung around this way. Just if you figure this thing's just kind of hanging here and we swung it the other way. Now, mine's not drawn perfectly to scale, but that's kind of the idea. If this side gets swung around, there'd be a place where it would be 10 in length, and it would touch this bottom side. And it's possible that this was 23 and this angle was 25, but the angle right here would have to be smaller, be acute, be 76. And that's how this ambiguous case works, because depending on where this side actually falls, whether it's here or here, there's only two places it could be, but it could make an obtuse angle, it could make an acute. So the workaround, and this is all you really need to know, if you always find the angles from smallest to largest, you'll be okay, at least for all the assignments I'm going to give you. If you ever deal with the ambiguous case, you can look at all the little caveats and how to get through it. It's not really the intent of my class. I just kind of want to remind you how law of sines works and get you thinking about some of this geometry once again. But I'm not going to dwell on this too much. If you just go from smallest to largest with your angles, you should be able to work around this on everything I give you. The first homework problem you come to is someone in a hot air balloon and they're going over top of an interstate highway and they see a couple mile markers. Right? And we can actually figure out our altitude by looking at those 2 mile markers and taking some angles to them. And that's what they're going to do. They're going to figure out their altitude by doing that. There's a term in here from geometry that sometimes throws students off, so I'm just going to remind you real quick, and it's angle of depression. So if I'm looking out straight and that's horizontal, anything I come down from there is called angle of depression. So when you see that term angle of depression, that's all it means. If you're looking straight out and then you decide to look down, you call that angle from horizontal the angle of depression. And similar, something you'll see in some other stuff here. If you're looking horizontal and you decide to look up, that's angle of elevation. So if you see those terms, that's what they mean.